So this is, as Carsten mentioned, first time in the industry that we tested some, combined network using some realistic use case for 5G xHaul, so front haul, mid haul, and the back haul. And the test purpose is, the verify combined interoperability. So not separately SRv6, not separately timing, separately VPN, and so on. So we are using here in this example SRv6 as the transport to interconnect the O-RAN components. So O-RAN components are emulated like O-RAN radio unit, O-RAN distributed unit, O-RAN CU. So ensure compliance with the O-RAN working group number 9 specifications, and as well effective handling of the traffic, especially for the front haul, because front haul traffic was very strict requirements when it comes to latency, jitter, and so on. So what are the requirements? As specified by the O-RAN Alliance, working group number 9, here we see the requirements for the O-RAN front haul. And there are different categories of the O-RAN front haul. Most advanced is high 25, then high 75, high 100. So what does it mean, for example, high 75? High 75 is the O-RAN front haul for the full new radio performance with fiber length up to 10 kilometers range. Okay, so this is the definition. And high 100 and so on. And we wanted to verify if you can fulfill these requirements with the packet switch network using SRv6 as the transport. So key elements that we tested is, first of all, ITU-T G.8275.1 telecom profile for clock synchronization. This profile includes PTP over Ethernet to distribute the phase and the time of the day, and Synchronous Ethernet to distribute the frequency. So it's hybrid profile, so to say. Then we use packet classification for IPv6 and for the Ethernet classification to classify the front haul traffic into better class. So we use priority code points for Ethernet frames and IPv6 Traffic Class or DSCP for IPv6 traffic. Then we use the prioritization of front haul traffic, and we follow the IEEE 802.1cm TSN. TSN is time-sensitive networking profile A. I will explain these profiles, how does it work, to prioritize EC-pre traffic. And of course, prioritization of PTP traffic as well. So let's start with these time-sensitive networking profiles. So IEEE defined 2 profiles for the front haul. Here's the specification here, 802.1cm, and there are 2 profiles. One profile is profile A. This is profile A with no preemption. So we have some packets, in queue number 2, which is not prioritized. And this packet, we start to transmit this packet. And then we get the packet in EC-pre queue, so the prioritized queue. In profile A, the EC-pre packet needs to wait until the packet in the lower queue is completely sent out. Okay, because we started already sending out this packet, so it needs to, be sent out completely. After this packet in the lower queue is sent out, we can start to send EC-pre packet, high prioritized packet. So this is one profile, how it works. Then the second profile, TSN profile B, is using preemption. So what does it mean? So again, we started to send some packet in the queue number 2, which is not prioritized queue. Then we receive some packet in EC-pre queue, which should be prioritized. In profile B, we are able to preempt the sending of the first packet, yes? So we send a little bit of this packet, but the rest of the packet we stop sending. In the meantime, we send packet number 2, this is EC-pre packet, and after we finish, sending EC-pre packet, we start to continue to sending the previous packet. So profile B is better from the latency, jitter, and so on, because we can preempt the packet. But at O-RAN Alliance, we made an analysis, and the result of this analysis was that there is a difference between profile A and B only for the low speed interfaces. So when we have 1 gig interface, then yes, there's a difference in the latency between 2 profiles for the EC-pre traffic. But if you have 10 gig, 25 gig, 40 gig, 50 gig, 100 gig interfaces, there's no significant latency. The difference in latency is below 1 microseconds. So that's the reason in this test we have used profile A. So the topology that we show here is on the diagram here. So as you see, there's complex topology. We have some front haul part on the left side, and there's some mid haul, back haul part. This topology consists from the multiple vendors. Yes, so we have different vendors. You have on this picture here. I will not list all the vendors because maybe I forgot one or two vendors, but you have vendors on the picture. In this topology, in the fronthaul part, we generate the fronthaul EC3 traffic. So it's going from the radio unit, which is emulated, of course, radio unit by the Keysight, and then it's going to the distributed unit, which is again emulated by the Keysight. So we have some fronthaul traffic going over in the fronthaul part, which is the left side of this diagram. And then, in addition to that, we generate as well some background traffic, some additional traffic, just in order to saturate the fronthaul link. So we will test in the extreme conditions that the fronthaul link is saturated, so it's congested. And even in this congested situation, we'll check if the fronthaul traffic is, going through with low latency and so on. And then in order to achieve this, prioritization of the fronthaul traffic, every vendor that participates in the fronthaul part of the network is deploying this TSN profile A scheduler. Okay, so which means is EC3 traffic is prioritized to the highest possible level, and the background traffic, if there's congestion, the background traffic is delayed or dropped, but fronthaul traffic should not be affected. And as well, PTP traffic should not be affected. Now, let's discuss in more details this fronthaul 75. Yes, what does it mean, this fronthaul 75? The end-to-end budget, as an example, yes? The end-to-end budget for the fronthaul 75 is 75 microseconds. So it means latency from our radio unit to the distributed unit is maximum 75 microseconds, should not exceed 75 microseconds. And this high 75 is defined for the fronthaul with the distance or, fiber lengths up to 10 kilometers. So first of all, what does it mean, this 10 kilometers? So we could have fiber between RU and the first router, cell-side router and the second router is hub-side router or pre-aggregation router to the DU. So these three, segments of fiber is maximum 10 kilometers. 1 kilometer of fiber is approximately 5 microseconds. So it's more data is 4.9 microseconds. So 10 kilometers is 49 microseconds. So we use out from 75 microseconds, 49 microseconds for the fiber itself. So which means for the routers, what we have for these two routers is maximum 26 microseconds. So if we measure maximum 26 microseconds, it means that these two routers can be placed in the high 75 O-RAN fronthaul. All right. And then, we use some prioritization, as I mentioned. In this example, so prioritization settings are not standardized. So we just choose for PCP number 5. For IPv6 DSCP, we use expedited forwarding for prioritization. And based on that, TSN profile A prioritize this traffic with these prioritization settings. So test procedure that we follow, we provide network synchronization. So Björn after me will go into data for this network synchronization, time synchronization using 75.1 profile. And we, as I mentioned, we congested the fronthaul traffic, congested the fronthaul link with some background traffic, and in ensure we measured that EC3 flows were not affected. So the end results were, clock is okay, but Björn will discuss the clocking in more details. And the Y latency as well was okay. So this is the results that we measured during the Berlin testing, because we tested in Berlin one month ago. You see a couple of vendor pairs like Juniper and Ericsson fulfilled this 26 microsecond budget that we calculated before for high 75. Some other vendors fulfilled 100, so it's high 100, so it is 51 microseconds for this one. So which means currently the industry is in the position to place packet switch network for the fronthaul application as well, because even in the congestion, which is the worst, situation that you can imagine, even during congestion, we can add very low latency, and packet is, synchronization is not affected. So I will stop here, and I will ask Björn to have more discussion about synchronization aspect of this network.
Thank you, Christoph. So as Kanchen mentioned, we wanted this year to combine SRv6 with timing and not just do a separate timing testing here. So the topology that we tested and what Christoph mentioned is that we simulating traffic. We are putting simulation from Keysight with simulating the RU and the DU here, and the topology here. So what we are simulating is kind of a chain of boundary clocks that will show all the way with backhaul, with fronthaul, and here. So what we are running here is a full timing network with SyncE and PTP for 75.1. The other thing we also introduced this year was also to add in 800 gig for a PTP here that you see on the right side. In addition, we also are putting into the testing and demo here our interworking function. So you deploying our 75.1 full timing support, but some place of a network maybe not fulfill that requirement. So you need to do a 75.2 profile. So we have a demo in the setup here that we are going to show you the measurement between both a full timing network with G.82-75.1 and the .2 profile. The last thing and important thing from the operator for the operation part is the function of passive port monitoring. It's important that you can measure and see what is the difference between the timing sources on the network and how good are the boundary clock performing here. So we have also included the asymmetry detection and the measurement and the operational part with the passive port monitoring here. And lately here, we are also going to show you the measurement with the test equipment from Keysight and Calnex, that we are measuring both the two-way timer, the constant timer, but as well the relative timer between the nodes, which is an important thing in the fronthaul, as Christoph described here. This is the setup that we have in the back here, with all the vendors' equipment that shows from the right side the grandmaster through the different chain of boundary clocks, and as well the different measurement devices from Keysight and Calnex, and they will come into. As Christoph mentioned, on the upper layer, we are running traffic in the congestions between the Ericsson and the Juniper nodes. So there we have drop-out traffic in the best effort queue, and we'll kind of demonstrate that it's not affecting the timing and synchronization quality here. As you see here, between the two Juniper devices, we also have added in a device which adds in asymmetry. So this is for the passive port monitoring features that if you see here now on the screen, this is actually measured on the ACX at the end of the chain. And we added in 540 nanoseconds of asymmetry, and you see we are detecting minus 270. So it means that there are some asymmetry which you need and can compensate in the network here. So now we are going to show you. Oops, sorry. So now what we are going to show you is really the measurement points that we have throughout the network, both showing the two-way timer, the relative timer, and also showing the end-to-end delay here. Okay, here. So what you see down here in the phase offset in the middle with minus 278, this is seen from the Juniper device there, doing passive port monitoring on one of the interfaces. So this is actually comparing the offset to be towards the port is locked to up to the Ericsson device. So it detects the asymmetry that we added in through the device with 540 nanoseconds. So I will hand it over to Sayantan here now.
Thank you, Björnar. Now I'm going to show you two sets of measurement. First traffic and then time error measurement. So here you can see this 5 rows. So first 2 rows represent the best effort background traffic, which is basically running between a core and an access, and it's around 10 Gbps. And then the last 3 rows basically represents the Asymmetry frontal traffic. Row number 3 and row number specifically are for downlink traffic, and row 5 represents the uplink traffic. Now, we should take a look at the latency numbers here. So for the last 3 rows, if you notice, the average latency is below 20 microsecond. And if you look at the max here, it's not even touching the 26 microsecond that, Christoph showed you, right? Whereas if you look at the first 2 rows, latencies are much higher. Okay, so that is one important aspect. The other important aspect is the loss here. So here again, for the first 2 rows, the loss is 9% and 3%, whereas for the last 3 rows, there is no loss at all. Right? Now let me switch to some time error measurement here. So here what I am showing you is a measurement along the chain. Let me zoom in so that you can realize this is actually output from four different routers, starting from core, then pre-aggregation, then aggregation, and finally the access. And you can realize that how close they are to each other, right? And then let's take a look at the same thing on the SyncE side. And here also, if you just zoom it, and probably you will realize that it's peak to peak is not even 1 nanosecond. And SyncE is one of the reason of this very good PTP time error performance. And lastly, I want to show you the relative time error between 2 access Ps, and which is again within I would say plus minus 10 nanosecond most of the time. And so with that, I would like to emphasize on the fact that even though there is a congestion, it's not affecting, time critical services, 2 time critical services. One is the fronthaul traffic and another is the time synchronization itself. So now I would like to invite Kevin on the stage to show some more measurements. Thank you.
Thank you, Sayantan. Now, as Christoph was saying, the latency through the network is affecting the data packets. The timing that we're looking for is affecting the accuracy at the clock, at the far end, at the access router. So what I'm going to show you are measurements on 2 access routers. First of all, the SyncE. You can see the SyncE is locked at EPRC quality on both of the routers. One is Ericsson, the other is Juniper. The time going through them is very close, within plus minus 1.5 nanoseconds because of the enhanced SyncE. What that gives us on the time error, see the 2 routers are coming in, one's about plus 7 nanoseconds, one's about plus 8.5 nanoseconds. These red lines at the top show that some packets are missing somewhere in the network. And I'm not going to go into much detail of those ones. Now, these 2 routers are running over a G.8275.2 connection with interworking from G.8275.1. So it's pretty good timing, including that interworking function. And we can have a look at the packet analyzer tool on the timing equipment. And you can see, apart from the inter-message timing, everything else is coming up with green flags. The interworking, the protocols are working well on both devices. So I think we can say, yep, the timing's working well. Coming back then to the relative time error, as Sayantan was talking about, the relative time error is sitting in the region of, plus 5 down to about minus 2 nanoseconds. Again, I'm sorry about the red lines. That's coming from some packets missing upstream of the test equipment. And with that, I'm going to hand back to Bjorna to summarize.
So I think this demo here kind of shows a typical deployment that our operator would like to see, and we kind of have demonstrated that building a packet-based network for fronthaul together with timing and all the services with congestion that is working. So I think it was a great effort between the SRv6 team and the timing clocking team at this EANTC testing here this year. So I really think it was a good thing. So if you're curious, go and look on the EANTC webpage for the full report. It's a lot of more comprehensive and interesting test cases for all the segments. Thank you.